What's good? So today I'm going to be going over a radical reaction, specifically homolytic cleavage of pi bonds using a peroxide radical initiator. So you should already be somewhat familiar with radical reactions, or at least the mechanisms and how they work. If you're not, I would go ahead and review that before watching this video, because this is specifically going to be dealing with the usage of specifically benzoyl peroxide as a radical initiator. So before I go over this mechanism and all this stuff, throughout this process, I want you to be thinking about what kind of product we're going to obtain. Will we obtain a Markovnikov product or an anti-Markovnikov product? That's something you're going to want to really be thinking about during this mechanism. So here we have our reaction mechanism set up. We have this carbon molecule here. We're going to be using HBr. Our radical initiator, ROOR, and I'll show you in a second. This is actually benzoyl peroxide and light. So like I said, I first want to go over our radical initiator. So this is what ROOR stands for in this case. As you can see, we have this molecule here. You should notice a couple things about it. First is that we have two oxygens bonded to each other. Those two oxygens are bonded to each other with one molecule, or with one bond. And finally, if we were to split this down the middle, we would have identical molecules. And this is very important in terms of the formation of our radical. As I said before, this is a radical initiator, and it is a benzoyl peroxide molecule. In general, for this type of reaction, you can use any peroxide, but in this case, we're using benzoyl peroxide. All right, so now after looking at this, we can begin the mechanism. And all mechanisms for radicals involve three steps: initiation, propagation, and termination. In terms of this sort of setup of question, you'll be using the three-step method. All right, so let's begin with the initiation. So like I said, our ROOR group is going to be the radical initiator. So we're actually going to draw it out like this. And this is because we're going to cleave this molecule, and we want to cleave this molecule so that it produces two identical radicals. And this can be done by the following reaction. And again, you should know to be using half arrows because they signify the transfer of only one electron. And what we did is we essentially just cleaved this molecule and gave each of these oxygens a radical. And of course, we achieve this using light, and we're going to obtain two RO radicals. All right, so this is a very simple way to start. As you can see, all we did was cleave this initial molecule so that we obtain two identical radicals. Again, this is homolytically cleaving, and there's a fly, sorry. So once we have these two radicals, we can actually continue to create our bromine radical, which is really what we're after here. So I'm actually going to do it down here to show the formation of our bromine radical. Remember, we do have HBr. And this is how we're going to produce our bromine radical. So we're first going to start off by putting an arrow to the bromine. This is what's going to actually give us our bromine radical. And we are then going to bond this oxygen to this hydrogen by joining these two radicals here. So we're going to do that and that. And from this, we will obtain boom. All right. So this is the answer for the next step, the creation of the bromine radical. And again, this is really what we're after here, this bromine radical to begin the propagation step. But just kind of reviewing our initial initiation step, we started with cleaving the peroxide using light to obtain two identical radicals. We then cleaved the HBr in order to obtain a bromine radical, and then bonded the remaining hydrogen using the radical of the peroxide. So Here's the initiation step, and at this point we can continue to the next step, which is the propagation step. Now, before we begin the propagation step, I'm going to draw out the initial part. So this is probably the most important part of this problem because it revolves around the topics of stability and Markovnikov or anti-Markovnikov product formation. So let's begin by examining this molecule. As you can see, we have two carbons connected to each other with a pi bond. The carbon here at the apex, and there's a carbon here. Now, thinking about stability of carbon molecules, we know that when we have something like a carbocation or a radical, we want that radical to be on the more substituted carbon. This is because it's going to create the most stable molecule. Again, this is true for both carbocations and a more simple example, but also radicals. The same rule will be followed with radical formation. You want the positive or the radical charge to be on the most substituted carbon. This means that knowing the idea of stability, we can actually determine at this point if this will be a Markovnikov or an anti-Markovnikov product. So I'm going to give you like 3 seconds to pause the video and think about that. After saying that, think if this will be a Markovnikov or an anti-Markovnikov product. All right, so I'm going to draw out this mechanism, not tell you the answer just yet, just so we can get through it. All right, so we're first going to start off by cleaving these, by creating a radical here. So this is going to go here and form a bond with this bromine. This is the actual bromination of the molecule. But now we have one radical left. Where does that go? Like I said earlier, we want that radical to be placed on the most substituted carbon, meaning it's going to be that one here. I know it's kind of weird to see with the arrows, but it's going to go on this carbon here. So we can now draw what is essentially our product. So let's go over this really quick. Our radical went on the most substituted carbon, which would be this one here, and we attached the bromine to the other carbon on the end. Thusly, we can conclude that we have obtained an anti-Markovnikov product. So we can again further deduce that by using peroxides and radical reactions, we can achieve, it's another way of achieving anti-Markovnikov halogenation of a pi bond. So I'm just going to draw this here. Just to denote that we have attained an anti-Markovnikov product specifically. All right, so we're not done yet because we still need to deal with this radical here. So I'm actually going to draw it down here just so it's a little bit easier to see. And we're actually going to cleave another HBr molecule so that we can get rid of this radical here. So we're going to follow the exact same process of this cleaving this way. I'm putting that there. Thusly giving us our final product for the propagation step, at least. There you go. Sorry, this isn't good to me. There you go. So there's that. This is, we have obtained our essentially what our major product is going to be. This molecule here. As you can see, all we did is we brominate, one moment. We obtained a bromine radical and this molecule here. We formed a bond between this radical and this radical with a hydrogen, and then just, a normal bromine radical. Now, we are not done yet because the final step is termination. And there's actually 2 ways to do this. One involves simply forming a Br2 molecule, and that is done in the following manner. Very simple. Very, very simple. Br2 formation. That's one way, as this is the one being consumed. Or we have a different fashion of creating a termination step in which we actually use this radical here. So I'm actually going to star that, move that down here. So let's draw out what we had up there. We had this, and we had a radical. So before, what we did is we cleaved the hydrogen from the HBr bond, and we added a hydrogen, essentially giving us this product here. Obviously, we don't even have to show the hydrogen in this case. But what we can actually do, remember that we do have bromine radicals available for usage after that step, or sorry, up here, we do have bromine radicals available to be used. So what we can actually do is this. We can brominate this molecule even further and obtain this as our termination step. So yeah, there's actually two ways of terminating this. One in which the carbon radical abstracts a hydrogen from the HBr, or the one in which two radicals come together to make a bond and end the propagation of the chain. So yeah, there's two ways of ending this. So that's actually the solution to this problem. I'm going to sort of put this up here. First, we cleave the R-double-R group. We obtain our bromine radical. We then cleave the pi bond by attaching the bromine on the least substituted carbon and thusly attaching the radical on the more substituted carbon, giving us an anti-product. We then abstracted a hydrogen to obtain another bromine radical and the final product, or we could go in a manner in which we actually use the radical of that molecule to brominate it again, thusly ending the chain. So yeah, there's this for you. I'm actually going to leave this board in the comment section or wherever I don't care, wherever it is, just so you can kind of play with it. But yeah, this is the answer. I'm probably going to do another radical reactions problem soon, and then I'm probably going to do a synthesis involving probably aromaticity rules. I feel like that'd be pretty useful. But yeah, hope you enjoyed. If you like this, if you want to see more stuff like this, just tell me. But yeah, I hope you enjoyed this. Hope you found it interesting, and I hope that you can enjoy chemistry as much as I do. Also, the Mosaic by Capstan came out today. Super duper hyped. I think Empire is really good. The breakdown with like the drill, like so good. I think Capstan is kind of similar to Belmont. I think Wilmette, Belmont, and Capstan are very similar in their music